Okay, guys, so here we are, week 5. I'm still trying to get that PV Watts link to work. Let me just show you where it's supposed to go. And for whatever reason, so it's topic 3. It's the PV Watts version 1, and it just keeps taking me back into the shell. But anyway, this is where it's supposed to take you. So I'm going to copy that URL. I'm going to come back in here. I'll just go back and I'm going to edit the link itself. I'm just going to paste the URL right in there. So if worse comes to worse, just cut and paste that. That might even take you there. I'm not sure, but just that's where you want to go. And I don't know why the Moodle shell's acting up. But. Okay. I'm going to go back up and see questions. I don't see anything from topic 3. System components. So let's just catch up on week 4. And I'm mainly treating these lectures as just kind of catch up on the forum. But it looks like nobody had any questions on week 4. Okay. If you want, well, in fact, next week I'm not here, and so here's what I'd really like to have happen next week, if possible. All the way down at the bottom of the shell, there is a practice exam. Let's just go down and take a look at this thing. Yeah. NABCEP practice exam. So let me open that up right now, if I can. This is section 16. Let's just take a quick look at it here. There's 2 of them, the NABCEP Practice Exam 2, NABCEP Practice Exam 1. So I know this is a little premature for the course, but hopefully this gets rid of a little bit of test anxiety. So it sounds like you guys are pretty well caught up on the rest of the questions. Well, maybe not. It was 30 minutes. I thought it would just let us right in there. Oh, the edit quiz. Okay. We might just be able to look at it through the editing mode instead of the.
Is the actual NABCEP quiz going to be online, or is it?
I don't know. I think it's going to be sit down, pencil, paper. Yeah.
Naomi, who's going to be?
Yeah, Naomi's the proctor. Let's just look at the first one here. Yeah, I don't mind looking right at this thing. So, first of all, 120 volt, 100 watt light bulb draws how much current? You guys want to just take a crack at that while we're sitting here? This is kind of right back to your AC too.
How much current?
Yeah, you're looking at 120 volts
100 watts.
and 100 watts.
Yeah, we have the resistance and we have the.
Well,
That's what I'm getting. Is that what you guys are getting?
1.2. I might have arranged that. Is it I equals P over V or V?
Well, P equals IV. So solving for current.
Oh, whoops, yeah, I just put that.
Yeah.
Put the watch for the.
It's so you look for the easiest answer, like, oh, just divide, 120, yeah. So, again, and you know, if you are taking these things online or even written down, and you think you got the answer, just write it down this way, and you can go back and check it. Yeah, that was kind of too simple to miss.
We're not gonna be able to have anything with us when we take that, right?
You know, I can't even remember what kind of, if you get any open books or cheat sheet or anything.
Definitely gotta figure out. We want a note sheet.
Yeah.
Formulas on it can be very beneficial.
Naomi has run it before.
Just see her, maybe ask her.
I'm gonna let you guys be in charge of that. Yeah, just I don't want to get in the middle of that one. Yeah. Okay, how about this one? Blank is the amount of time a fully charged battery system can supply power to system loads without fully charging. Blank is the amount of fully charged amount of time.
Is this a multiple choice or do you just have?
Yeah, I'm almost positive this is multiple choice. Let's just kind of cruise down here. Duration, capacity, autonomy, and standalone period.
Yeah, something else capacity. Autonomy doesn't really make any sense.
Autonomy does not make any sense, but check it out. That's the answer.
Really? Okay. Better read the battery chapter.
That's a new one on me. Actually, let's look it up in the book. I want to see that.
The amount of time a fully charged battery system can supply power to system loads without further charging.
Well, good to know.
Is that
Page
the
483 in the glossary.
is that the glossary? Nice, nice, nice.
So let's see the index of what chapter that is.
Battery's acting of its own volition.
It's a strange word, isn't it? When I think of autonomous, I think of control rather than just power.
Yeah.
It's on page 164 and 260. Let's check out 164 first.
6.
164, you see?
Yeah, bottom corner, hey Wally. Bottom corner of 164 says autonomy. In standalone PV systems, battery capacity is generally several times than needed for the average daily load in order to account for days with below average insulation. And it says autonomy is the amount of time a fully charged battery system can supply. That's Autonomy is expressed in days or sometimes hours. 2 to 6 days. There we go. You boy need some? Okay, there you go. Don't miss that one. I'll just go through this first one, and then I'll have Guccio take you through the second one. To increase battery voltage, blank.
Increase the current.
Use bigger cells. Wire more cells in parallel. Wire more cells in series. Not possible because of absolute limits. Well, so you guys know this one already from your DC. To increase voltage.
That's how those jumpers work.
So let's just go over that. So if we've got let's just do a couple batteries here. 12 volts. I used to have a cool selection tool. I have battery babies here. Okay, so if I've got 12 volts and I have well, let's see. Let's just do plus, minus. Plus minus. So if I wire them like so, let's put my multimeter right here, and if I wire them like so, 1, 2, 3, 4. What's my voltage on my multimeter up here? 24. There we go. Because they're wired in series. Otherwise, if I wire it like this, they are wired in parallel, right? Plus, minus. I guess I would actually. This guy would come over here and attach the plus, right? This guy would come over here and attach the minus. You're still going to have your 12 volts. Right, you'd be able to potentially get more current out of the one that's wired in parallel, but this is obviously series, and this is parallel. The other way to draw this, the circuit way to draw this would be to have your batteries like so, batteries like so. And so if you've got this guy at, we're just going to call this V naught. If this is V1 and this is V2, we just know that V naught equals V1 plus V2 versus, and that's this versus this. Right, these are 12 volts. 12 volts. No matter where you put your leads, here, 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 you're always going to get your 12 volts. So, draw it out, convince yourself both ways. Okay. That's not too bad. Okay, this is, you will almost certainly get a question like this. Standard test conditions. Rates module performance at an irradiance of blank watts per square meter. 800, 1,000, 1,500, 2,000. The solar constant above the atmosphere is like 1,386 watts or something like that, but, and once in a while you might see 1,500 watts, but that's super high, watts per square meter. And 1,000 is just sort of taken as the standard. Pretty easy to remember, too.
1,500 obviously, so that's not realistic.
Yeah, totally.
Okay.
These numbers just never happen. Be closer to the sun.
A blank is a PV device consisting of these are softball questions, gosh. Is a PV device consisting of a number of individual cells connected electrically, laminated, encapsulated, and packaged into a frame. Let's check it out. An array, series, element, module. Yeah, so the individual module is, the word panel isn't there, but panel equals module. You don't hear that too much, but solar.
And then an array is just a series of modules?
Yeah.
4 or more, I think, or 5 or more. So.
I think even if you've got 2 modules, that's an array.
Is that an array?
Yeah, it's a pretty small one, but yeah, I think this.
I remember glancing over that.
What you need there, Wally?
Well, my clicker for my slideshows disappeared. I
Oh.
had it yesterday in class, right?
Yeah.
I was clicking.
Hmm.
Wasn't me. I wasn't there. I didn't do it.
No, that's a, no, should know what that is. That's a solder sucker.
Guys, so a blank curve is a graphic representation of all possible voltage and current operating points for a PV device in a specific operating condition. You heard this one before?
Can you do the screen like one Zoom?
Oh, for sure, yeah. Oh, yeah. So a blank curve is the graphic representation of all possible voltage and current operating points for a PV device at a specific operating condition. Yeah, it's called the IV curve. I don't think we've covered it we will cover that. Actually, no, we covered that a little bit already with the maximum power tracking. Let's take a look at. There might even be something on the CD. Let's take a look. Let's take a look. Taking a while to open. I thought the PDF might have an IV curve or two on it. Let's just go out here for a second.
Sounds like the best power.
Yeah. So this thing, and I'm almost positive I'm going to get a new. I think I might have covered this. Yeah, I did. I covered this briefly in week 2. So if, and again, if you remember back, power, and I already wrote this down, power is just volts times amps. Volts is the across variable, amps is the through variable. So in the case of a module that has an open circuit. So let me just draw what that is. So let's just, here's your module. There are many cells in series, but what you've got is two electrodes in and out. If there's no load across that, you're going to just put your multimeter on there and measure what's called the voltage with the open circuit. So there's no load on it whatsoever, and it should be pretty high, depending on the panel type. And that voltage is basically right here, where there is no current. But if you go back and multiply volts times amps, and you have no amps, then you have no power. The other configuration is to take the two things together, put your multimeter on there, and just measure current. So this is ISC, so you'd have an ammeter on there, and you're just basically letting current flow through with almost no resistance. Like, how much juice can that thing make? Well, where's that? It's down here, so you got all kinds of current flowing through, but no voltage. So this curve is just called the IV curve. I for current, V for voltage, will give you the all the different voltages at a corresponding current or vice versa. This P3 that I've drawn here is the maximum power. You're maximizing the size of that rectangle, because the little black one, when you've got very low current, the P1 is that rectangle. It's small. So the red rectangle, although it's long, it's also got small area. So the green one is the largest. Okay. And it looks like the site survey, charge controller profiles, interactive system sizing. Yeah, take a look at these. Take a look at these PDFs. I'm just kind of digging through the CD.
Those are different charts that go inside the top of the sun kind of thing, the monitor and the shade.
This is not the this is more just straight out of the textbook. The Solar Pathfinder charts are going to look a little different. Not that much different. In the Solar Pathfinder, each one of these little squares is going to have some amount of time associated with it. So it's yes and no. It looks almost identical, but you couldn't just take this and turn it into power. I'm just going to see if there was something on here that had the okay, these are all radiation tables. That is a lot of PDFs. Omaha solar radiation, 41 direct beam. Burns, Oregon. Yeah, I think this would be available. PVS. Let's run one of these guys too. Solar calculator while we're at it. Clock time. Standard time. Let's do 1300. Let's do mountain. Let's just do today, February 23rd, 2016. What is the local longitude here again?
110 or something?
Was it 114?
Yeah.
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 114.
Oh, yeah. Oh, look at this. We can, calculate the solar time. This guy, that's pretty far off, isn't it?
Yeah.
Let's see, if we go to standard, calculate, 1022, 40 minutes. Yeah, so this gets us that same answer we're looking at, just with the little widget.
That
Cool.
was on that beacon on the disk.
Yeah, this is all on the disk.
We had no.
I got time on this. It wasn't back in the book.
I would play around with this a little bit too before your test, and also do that same calculation we did last week. You know, anything like that was slowing you down. Lots of worksheets. Yeah, take the quick quizzes. Cells, modules, arrays. Nice. Nice. Photons of light. I like that one.
What is it like?
Entire thin layers.
Thin film?
Gosh, I don't even know the answer to that one.
Of course you do. Now you've got to ask us if we know.
I don't know. I don't know where to go with this one. Module level PD device with its entire substrate coated in thin films,
I think it's thin film.
thin layers.
Polycrystalline is the most common type of PV cell, I think. It's just made out of reaction silicon crystals, and there's monocrystalline, which is grown out of one huge crystal.
Yep. Yep.
They're more efficient, right? But like harder to.
Usually the mono is gonna give you a higher efficiency typically.
Well, I mean, multicrystalline, I think you can rule that out.
Page
The same
127, it's even cell material, because that's efficiencies.
127.
Polycrystalline is the one that's on there. I mean, there's others, but not any of those other answers.
127?
At the bottom there, there's a chart just talking about material efficiency.
Oh, entire substrate coated. Poly-multi. I was going to go with amorphous. Thin layers. Let's just try thin film. There we go. I think, yeah. I was going to go with amorphous, and in fact, we've got some, we had some in here. They might be next door. But the, let's just look for a picture of one here. Thin film PV. Let's see what the images come up with. Yeah. I think the giveaway there was entire surface. If you look at this guy, you don't see the individual cells. That's the difference. That's where he's going with it. So I would have called this amorphous, but thin film. Okay, fine.
So is that actually just one big cell, or are there cells hidden under the coating?
That's a good question. one big cell or there are multiple? I think they're going to be multiple. Otherwise, you're not going to hit the voltages you want, because each cell itself is just a half a volt or whatever. So there will be multiple cells in there. Just it looks as if the whole thing's coated, because more or less it is. Yeah. Cool. A blank is a thin, flat disc or rectangle of base conductor. I'm going to call that wafer. Yeah? Is that jiving? Wafer? The array is the big one. Plate, it's not a term. I mean, it's not a technical term that I know of in PV. So the wafer is the actual conductor that's semiconductor that's sliced out of the crystal. The blank is the basic electrical output of a PV device. Better be this. Yeah. Yeah. The open circuit voltage is just one tiny portion of the IV curve. The basic IV curve parameters include the open circuit voltage, yep. Short circuit voltage, yep. Maximum power, better, all the above, okay. Nice. Changes in solar irradiance have blank effect on the current output of PV devices. Better be significant. It's the voltage is not going to change much. Right, so the voltages will kind of either be on or off. You know, once you hit a certain photon level, here comes the voltage, but it's not until you get a bigger stream. And the way to think about that is just kind of back to our across and through variables. So, you know, here come the photons coming in. I'm just going to draw them as little phe's. And each one of these photons represents a certain amount of energy. And as I said before, if you're getting a critical number, you will get to the voltage, like you will measure some voltage. But unless you're getting a whole bunch of them, you're not going to get that much current. So the number of photons hitting that are affecting, kicking the electrons up into the active Fermi shells within the semiconductor, and just the more times they come in, the faster the electrons fly around there is current. Okay. Cool. A blank is a PV device consisting of a number of individual cells. That's the module. Yeah. A blank is a device used to pass current around rather than through a group.
Bypass diode would be my guess.
I would guess bypass diode too.
I don't know. Right zone.
Let's look at diodes in here. I'd like to ask Wally how frequently these diodes fade, because that can mess with your system. Diode.
And that's just to prevent the voltage from back.
Yeah, the diode keeps the current from running backwards through the system, exactly. I'm just going to look at diodes here in the book. So 326 to 327. 326 to 327. All right, so right here on page 326, blocking diodes. Diodes used in PV source circuits to prevent reverse current flow. For example, in a single or a simple self-regulated PV system, a fully charged battery, may begin to discharge through the array when the array voltage falls below the battery voltage at nighttime. Okay, so that should make sense. Let me draw that up here. So if you've got your, and I'm just going to draw this super simply. If you've got, I'm going to leave out the charge controller and the inverter and all that for now. I'm just going to put in the battery and the array. Somewhere in here you would also have a load, of course, but if this V array or V module, however you want to look at it, if V array is greater than V bat, you will get, well, that's what you want. You want the voltage to be greater and to flow into the batteries. But if the voltage of the battery is greater than the voltage of the array, you get current in this direction. You do not want that to happen. It's just going to drain your battery because the array itself is a resistor, and you're just heating up your resistor for no reason. So that's the reason for the blocking diode. Now the bypass diode, let's read that one. A bypass diode is a diode used to pass current around rather than through a group of PV cells that are shaded. There we go. In contrast to blocking diodes, bypass diodes are installed in parallel with modules or groups of cells. Each module may include 1 to 3 bypass diodes. There we go. Under normal operating condition, current does not pass through the bypass diodes. However, if the cell develops an open circuit or high resistance condition because of shading or damage, bypass diodes minimize power dissipation by the shaded cells, preventing them from overheating. Nice. And there's a picture of that. That's actually figure 1119 in the textbook. And I've seen this. If you're ever up the Rattlesnake and you go by the this is the Clark Fork Elementary School, they've got, I don't know, maybe 12 or so panels and modules, and 2 of them, by the time 1 or 2 o'clock rolls around, they're in the shade. So you definitely want your bypass diodes for that. Okay. There we go. Nice. 10 out of 10. Chapter 5. Yeah. So definitely go back and hit this thing, guys. I'm just going to take a little break here. I think we're a little over 30 minutes, okay?